Okay, this is study guide problems for test 1. And question number 1 is, what is the direction of electric field at a point a distance r away from a positive charge? Right? And the multiple choice question, it's directed towards the charge, directed away from the charge, no direction for electric field, and D is none of the above. But we have to know that for positive charges, electric field goes out radially outwards, right? In every direction. I can draw only a few arrows. For a negative charge, the electric field is coming in radially inwards. All right? So then for positive charge, it will be away from the charge. So, number 1, correct answer is directed away from the charge. Number 2, a charge of positive 2 coulombs, so his positive 2 coulombs, is located at -1, 0, and another charge of negative 2 coulomb is located at 1, 0. So -1, 0 and 1, 0. So this is for number 2. And positive 2 coulombs, negative 2 coulombs. We want to find what is the direction of the net electric field at 0, 0, that is at the origin. So from the positive charge, we know from above problem, it will go towards the right, that is away from the charge. So it will be in that direction, that is from this charge. For the negative charge, it should come towards the charge, so the electric field will also be directed in the same direction. So that means electric fields coming from positive charge and negative charge, both of them will be directed to the right. That means towards the negative charge. So the answer is towards the negative charge. Okay? So if you have reverse situation or other situation, you can think by yourself. All right? Now, number 3. A charge of positive 2 coulomb is located at -1, 0. So -1, 0. By the way, whenever I don't mention the unit, the coordinate will always be in meters, okay? In meters, right? -1, 0, 1, 0, etc. They are all in meters. So positive 2 coulomb is located at -1, 0. And another charge of positive 2 coulomb is located at 1, 0. So both of them are positive charges. What is the direction of the net electric field at 0, 1? So don't get confused. 0, 1 is x is 0, y is 1. So it's up here. This is -1, 0 on x-axis. 1, 0, so y value is 0. So it's also on the x-axis. X is 1. So I want to find the net electric field here. From this positive charge at -1, 0, it will be directed away from the charge, and same here, it will be directed away from the charge. But from symmetry, you can see that this is -1, 0, this is 1, 0. The distance from this point is 1, this is also 1, this height is also 1, so this is 1, 1, so you can see that it's square root of 2, this is also square root of 2. From symmetry, you can also see that the distances are the same. That means the strength of the electric field is the same, and you will see that this xy axis, on this xy axis, this guy will have two components, x component and y component, x component and y component. So x component of this guy is this direction, x component of this guy is in that direction. They will cancel out because they are in equal amount in opposite direction. How do you know the magnitude is equal? Because the distances are the same from here to here and from here to here. and the angles will be the same. Now, what about the y-axis? Then y component, the y component will be directed up. This y component will also be directed up. So both of them will be directed in the positive y direction. So they will add up. So the net direction, the direction of the net electric field at this point will be upward direction. That will be positive y direction, right? So it will be in positive y direction. So the number 3 answer is in the positive y direction. So you can imagine that if it is negative and this is negative, or this is positive and this is negative, or this is negative, this is positive, you should try all possible cases. All right. Number 4. A uniform electric field is directed towards the east. If a negatively charged ball is hanging with the string from a suspension in that field, the ball will swing A towards the east, towards west, towards the south, towards the north. All right? So the situation is like this. Without electric field, a negatively charged ball is hanging. Now you have electric field directed towards the east, right, in that direction. So positive charges will move in the direction of the electric field, and negative charge will move opposite to the direction of the electric field. So this ball will swing towards the west. All right? Okay? So that's the answer for number 4. Swing towards the west. So let's do number 5. So I have written it out so that it will not too long, because I did this video before. It took 1 hour and 15 minutes. So because I had to write, so I wrote it now ahead of time and explained to you. So number 5 is a charge of positive 2 coulomb is located at -10. So positive 2 coulomb -10 here. And another charge of positive 2 coulomb is located at -10. So it's by 10 here. Charge is positive 2 coulomb. What is the magnitude and direction of the net force on a charge of -3 coulomb? So -3 coulomb charge at 0, 1. So that is 1 meters above the origin, right? Okay, 0 means x is 0, y value is 1. Okay, so here. So obviously this is positive charge, this is positive charge, this is negative charge. So the forces will be attractive. So this will pull towards this and this will pull towards this, right? So there will be force here and force here on this charge number 3. So I call the force from charge number 1 to charge number 3 F13, and the magnitude is KQ1 Q3 by R13 squared. R13 is the distance between charge number 1 and 3. So from the figure I can see that this is 1 meter. From here to here is 1 meter. So then this is from Pythagorean theorem, this is root 2. Right? Pythagorean theorem is what? A, B, C. This is the right angle. Then C is equal to square root of A squared plus B squared. So K is 9 times 10 to the power 9. This is positive 2 coulomb. That's for Q1. Q3 is -3 coulomb, but I take the magnitude, and then the distance is root 2 squared. Right? So then root 2 squared is 2, 2 and 2 cancel out. So I get 9 times 3 times 10 to the 9 newtons, or 27 times 10 to the 9 newtons. It's a big number, but actually I don't want to use micro or nano so that you don't have to worry about those exponents. So the answer is 27 times 10 to the 9 newtons. Okay. And what about F1, 2, 3. That is charge number 2 to charge number 3, the force there. Well, it will be the same magnitude. Why? Because the distance is again root 2. This charge is also plus 2. And this is the same charge, negative 3. So then F23 magnitude and F13 magnitude will be the same. But anyway, so if you substitute, you will get 27 times 10 to the 9 newtons. Now, I cannot just add these two up and get the net force because I have to calculate the components. We already talked about it. The x components will cancel out because this vector can be decomposed into x and y, x and y. So x components will cancel out, y components will add up. Because this is 1, so that means this angle and this angle must be the same. This is 90 degrees, so each one is 45. So then I can find that the y component of F13 will be, F13 times cosine 45. So the answer is 19.1 times 10 to the 9 newtons. And similarly for the y component of F23, it is 19.1 times 10 to the 9 newtons. That means these two y components, each of them are 19.1 times 10 to the power 9 newtons. So two of them add up. So the answer net force is 38.2 times 10 to the power 9 newtons. Direction is in the negative y direction. Okay? So that's number 5. Now let's do number 6. Number 6 is 3 charges of positive 2 coulombs are located at minus 20, 20 and 02. So listen carefully. Minus 20, that's here, 20, that's here, and 02, that's here. So that's plus 2, and plus 2 coulombs, okay, here, here, and there. Now, 2 negative charges of minus 2 coulombs each are located at minus 1, 0, and 1, 0. So minus 1, 0, and 1, 0, they are negative 2 coulomb charges here. Okay? Now, what we want to find is find the potential at the origin. So, electric potential, I mentioned already in the past, is scalar, so you do not have to worry about direction. So, the potential at this point, the origin, all you have to do is add up all the potential from each charge. So the formula is kq by r. So V is equal to kq1 by r1 plus kq2 by r2 plus etc. up to kq5 by r5. So each of them you give the name and then the distance you can see from the figure. So let's figure it out. Here, k is the common factor, so I pull it out as a constant 9 times 10 to the power 9 Newton meter square per coulomb squared. Q1 by R1, let's call this Q1. Let's do the positive charges first. Q1 by R1, Q1 is 2 coulombs. R1 is from here to here is 2 meters, so 2 meters. Q2, similarly 2 coulombs. Distance is 2 meters, so 2 coulomb by 2 meters. And then here, this is Q3, 2 coulomb. This distance is again 2 meters. So 2 coulomb by 2 meter, 2 coulomb by 2 meter, 2 coulomb by 2 meter. And then for the negative charges, this is negative 2 coulomb. The distance is 1. And negative 2 coulomb, the distance is again 1. So negative 2 coulomb by 1, negative 2 coulomb by 1. So if I work it out, 9 times 10 to the power 9 Newton meter square per coulomb squared. 2 by 2 is 1, 2 by 2 is 1, 2 by 2 is 1. 2 by 1 is 2, 2 by 1 is 2. So negative 4 positive 3, the answer is negative 1. So the answer is minus 9 times 10 to the power 9 volt. So as long as you have potential, then you can just add them up because they are scalar. Not like electric field or force, they are not vector. For vectors, you have to consider direction. So number 7, I'm going to skip. Number 7 also give you 3 charges, and the same thing, find the potential. So all you have to do is use Pythagorean theorem, find the distance, and find potential using the same formula. Alright, so you can practice if you want. Now let's go to next number. That is problem number 8. Problem number 8 has several parts. So part A is I want to find the equivalent capacitance between point A and B. Okay, point A and B. So C1, capacitor C1 is 2 microfarad, C2 is 4 microfarad. So when capacitors are in series, the formula is 1 by CAB is 1 by C1 plus 1 by C2. So 1 by 2 plus 1 by 4, I get 3 by 4. That's not the answer yet because that is for 1 by CAB. So I have to flip this to get CAB. So CAB is 4 by 3 microfarad. Okay. For part B, I have this figure, which is C1 and C2 in parallel. C1 is 3 microfarad, C2 is 4 microfarad. So when I draw like this with angles, rectangular shape, or this way, doesn't matter, C1 and C2 are parallel. Here, this capacitor, let's call it C1 and C2 are also parallel. That means this type of figure is equivalent to or the same as this type of figure. Okay. Now C1 is 3, C2 is 4. For parallel capacitors in parallel, the equivalent capacitance is found by adding them up. So CAB is just C1 plus C2, which is 3 plus 4 is equal to 7 microfarad. So that's very simple. For problem part C, for 8, I have C1 and C2 in series, C3 and C4 in parallel, and then the two guys, C1 and C2 in series, C3 and C4 in parallel, those things are again in series. So equivalent capacitance for C1 and C2 together is C12, and the equivalent capacitance for 3 and 4 together is C34. To find C12, since C1 and C2 are in series, I have to use 1 by C12 is equal to 1 by C1 plus 1 by C2, which is 1 by 2 plus 1 by 3, which is common denominator 6. 2 goes into 6 3 times, 3 goes into 6 2 times, so you add them up 5 by 6. That's not the answer yet. So C12 is equal to 6 by 5 microfarad because I have to flip that. Now for C34, C3 and C4 are in parallel. That means the formula is C34 is equal to C3 plus C4, straightforward adding, and 2 microfarad plus 4 microfarad. So I add them up, I get 6 microfarad. Now after that I have C12 and C34. Now C12 and C34 are in series now. So CAB is equal to 1 by C12 plus 1 by C34. C12 is 6, C34 is 6 by 5. So I have to add them up like this, 1 by 6 plus 5 by 6, which is 1. So CAB is 1 microfarad. So after all this work, the answer is 1 microfarad. 1 microfarad, that's for part C. Now for part D is longer. part D, I have this figure. C1 and C2 are in parallel. C3 and 4 are in series. But whatever you get out of C3 and C4, that will be in parallel with C5. So it's like this. These two are in parallel. The resultant one is C12. C3 and C4 are in series. Their equivalent one is C34. And C34 and C5 are in parallel. After that, then I still have C12, and then this and this parallel, I call it C34, 5, right? This all three together, so that's here. Then after that, C12 and C345 will be in series. So this will be the net one. CAB is C12 and C345 in series. C12 is C1 and 2 parallel. C345 is C34 and C5 in parallel. C34 itself is C3 and C4 in series. So let's calculate C12. C12 is C1 and C2 in parallel. So 2 plus 2, I get 4. C34 is C3 and 4 in series. So I calculate 1 by C3 plus 1 by C4. So 1 by 2 plus 1 by 2, which is 1. Okay? So C34 is 1. So now what about C345? C345 is C34 and C5 in parallel. C34 is 1. C5 itself is 2. So 1 plus 2, I get 3 microfarad. So now CAB, the final equivalent capacitance, is C12 and C345 in series. So I already know C12, 1 by C12, and 1 by C345 in order to get 1 by CAB. So C12 is 4, C345 is 3. So common denominator is 12. 4 goes into 12 3 times, 3 goes into 12 4 times. So that's 7 by 12. But CAB, I have to flip that. In order to get CAB, I flip this. I get 12 by 7 microfarad. All right.